When we talk about the roots or zeros of a function, not just a polynomial or rational, but any function, we can think of that as being sort of a special location in terms of the relationship that the function might model, if we think in applied context. Something like the requirement in order for a population to hit zero, or the amount of time it might take for a falling object to hit the ground, or get caught in this case. And that kind of extends pretty generally. We can think of really any function, any point in a function as being some specific location that we want to know about for whatever reason, whatever thing the function might model. But it's not always guaranteed that we want a single specific point. We might have reason to look at many things at once. We might have reasons to look at ranges of things at once. For example, it has been said that a equation, a function of form g of x is equal to 0.0875 x squared plus, oh, not 0, oh boy, that's inky, 1.9x plus 11.6 can model the stopping distance required in feet for a car driving over wet pavement at x miles per hour. And in that sort of situation, it's good, I suppose, to know that if you're driving 50 miles per hour, you need 500 feet of stopping distance. I don't know if that's exactly what that formula says there. I'm just spitballing. But realistically, when you're in your car, you're not going to have somebody in the passenger seat who's going to whip out the measuring tape and make sure that you're staying exactly the right distance all the time away from the car. And for that matter, when you're driving, especially if it's in the rain when the pavement is wet, you probably shouldn't be using cruise control, so you're not going to be going at that constant speed there of 50 miles per hour or whatever it might be in those conditions. So it's nice to know that exact specific location in the sense of knowing an exact specific root or zero, but more realistically, you want to know at least how far away you should be for at most some speed that you are thinking of going to get from place to place. And with this sort of thought in mind, with this idea of wanting a range of values in mind, we can talk about inequalities again, where we had these at the end of chapter 1, and a lot of what we're going to see here is very similar to stuff we had at the end of chapter 1, except now we're going to assume you guys are a little more comfortable with the interval notation and number lines, but instead of thinking about finding some specific choice place, we talk in terms of ranges, where we'll start here with polynomial inequalities. These are things of form f of x is less than, at most, at least, greater than some value, where usually we center it around 0, just to be sure, because we're keeping in terms of that 0 value. It's an important one where that function f of x has the form an x to the n plus an minus 1 x to the n minus 1, and so on, however many n's it has in there for the degree of that polynomial. So if we're thinking about this thing here, we might not be so interested in knowing the exact value for something, but we might instead want to know how fast you should go in order to keep that stopping distance at most 100 feet. Or, thinking in terms of that sort of zeroed out arrangement, and I should have closed the marker, but that's okay, we could instead think about trying to arrange this in such a way that 0 is at most 0.087, there should be a 5 in here, 5x squared plus 1.9x minus 88.4. That we might be more interested in finding out when that happens. At the very least, it sets us up for our notation there, where in order to do this, we have a few steps we can follow. We're not always going to follow all of them to the letter, but this is what we can do generally, where we start by rearranging, like I did in that first case. We put the inequality into a form where a 0 is isolated on one side, and often we'll try and isolate it on the right, but you can do it on the left like I did. So you have something of form f of x less than 0, bigger than 0, and so on. Then from there, you solve the associated equality f of x equals 0, and locate the solutions for that on a number line. Or those are things called boundary points or boundary values that I'll talk about in a second. Then, in each of the sections that you've broken off using those solutions, you pick a point called a test value, where the test value is going to be your representative for the behavior along that entire interval. Then, if you have that f is positive at the test value, that would mean f is positive for all values in the interval. If f is negative at the test value, then f is negative for all values in the interval. And finally, you write your solution set, your set of possibilities that fit the conditions you want in terms of interval notations, where the boundary points, the boundary values, are those that occur at the boundaries between what we want and what we don't. That is, they're the places where a value can change from being positive to negative or negative to positive because, as we saw when we were talking about things like the intermediate value theorem, if you've got a nice continuous function, it can't jump. It's going to be what we need, provided we identify our zeros properly. You can only have those changes at those places. As you can see with this graph, that there's only the two spots in there where it can go from positive to negative or negative to positive. And to understand this a little bit more, we're going to take a couple of examples here.